DAOS is an open source scale out object store designed from the ground up to deliver extremely high bandwidth IOPS and low latency IOs to the most demanding data intensive workloads. DAOS supports multiple application interfaces, including a parallel file system, Hadoop Spark connector, TensorFlow-IO, native Python dictionary bindings, HDF5, MPI-IO, as well as domain specific data models like SEGY. With an overview of the DAOS architecture and the software ecosystem, we have with us Johann Lombardi, Senior Principal Engineer at Intel. Let's watch Johann speak about DAOS, accelerating AI with DAOS storage.
Johann Lombardi from Intel. I'm a senior principal engineer inside the supercomputing group. It's a great pleasure for me to be there and to present at SODACODE 2022. This talk is about our newest distributed object store called DAOS and how it can accelerate AI workloads. The DAOS adventure started back in 2012. I'm going to come back to the project history. Then I will present one slide on the DAOS architecture. DAOS is a very broad project with innovations in many areas. For the sake of time, I have decided in this presentation to focus on 4 architecture choices and 1 future direction. I will then present our rich partner ecosystem. There are several DAOS production deployments underway, but Aurora is by far the biggest one. I will thus spend some time presenting the DAOS configuration on Aurora. I will then finish with some generic resources about the project. Let's start with a bit of history. The DAOS project started a decade ago and was funded through several projects from the US Department of Energy, DOE. We started in 2012 with the Fast Forward project. Our charter at that time was to define the requirement for the next-gen distributed storage for Exascale HPC and AI. We prototyped DAOS over the existing storage stack based on Lustre file system. During this project, we quickly realized that we were limited by the performance of the legacy software stack and that developing in the kernel space was a real hurdle to adopt some of the new emerging technology like persistent memory and NVMe. That's why, in 2015, we restarted the development from scratch of DAOS as a standalone user space storage systems. In this ESSIO program, we also added support for persistent memory. This project was also the opportunity to get into regular release cycles with the v0.1, 0.2, and 0.3 version. At the end of ESSIO, we had a stable code base that was then used for 2 subsequent projects. In ECP Path Forward in 2017, we investigated what it will take to embed the DAOS engine on an SoC FPGA. That was a research project from which we learned a lot, and some of the features developed in this research project will find their way inside the mainstream DAOS under the form of active storage support. The second project was the co-role NRE, non-recursive enhancement, which was the big productization project for the Aurora system. In this project, we hardened the DAOS codebase and added a lot of new features for AI and big data. Under this project, we also created v1.0 version in 2020 that was used by several partners for integration. We then released in 2021 v1.2 that started to be broadly used, and in mid-2021, Intel officially announced L3 support for DAOS. This means that support contract can be signed with Intel to provide L3 support for DAOS installation that include code change and new releases. Around that time, we also started to submit at the IO 500 challenge in order to demonstrate the capability of DAOS. We are now on DAOS 2.0. We released 2.0.0 in December 2021 and subsequent bug fix release early this year with v2.0.1, 2.02, and we are working on 2.03 that should be released in the next few months. Meanwhile, we are working on future version of DAOS 2.2, 2.4 with a pace of a new release every 6 months. DAOS is a completely open source project available on GitHub. There is no enterprise version, hidden branch. Everything is publicly available. Let's now have a look at the DAOS architecture. DAOS is a scale-out object store that aggregates the storage distributed across many nodes into a global namespace accessible through the fabric by scientific applications. As represented in this diagram, we have been working for almost a decade now on the software ecosystem. This includes support for legacy application over POSIX, but also accelerate next-gen workflows through a tighter integration with HPC I/O middleware, AI, and big data frameworks. DAOS is built from the ground up for performance and scalability. It has already demonstrated tens of microsecond latency for both read and write, and can deliver billions of IOPS with very high bandwidth to the most demanding applications. Both the client and the server are written in user space for both ease of use and also ease of development. DAOS can run on-prem or in the cloud. It is particularly friendly to run DAOS in a container, Linux container. DAOS has a very modular layering and API that make it easy to add new features. It can leverage the latest hardware technology like persistent memory, Intel QET, InfiniBand, high-performance Ethernet, zero-copy I/O to from GPU, DSA, and also the latest software technology like LibFabric, UCX, SPDK, or ISAL. Support for self-healing and erasure code is done over the network, and the data placement can even be aware of the fabric topology. As I mentioned before, it is a fully open source project with a growing community. We have a user group around SC that gathered last year more than 150 developers. As I mentioned before, let's now look into 4 architecture choices we made in DAOS and 1 future directions. The first architecture choice we made early on was to introduce the notion of dataset in the data model. A dataset is called a container in DAOS, and that's the basic unit of storage for the user. A container has a type and can be a set of files per process generated by an application, for instance, a POSIX namespace gathering all the ResNet 50 images, an HDF5 file, or an S3 bucket, for instance. Users can snapshot each container individually, tweak many parameters like the data protection scheme for the data in the container. They can set different access control lists to share the container with other users. They can also, for instance, decide to enable compression or encryption on the container. The overall idea is that you have way fewer containers to manage than files. Storage now becomes easier to manage. Users can also run complex query against the list of containers or migrate a container to a different storage tier. In addition to the notion of container, DAOS comes with a new baseline API implemented by libDAOS. The DAOS API is very rich and has native support for arrays, key value store, and can leverage RDMA whenever available. It can support complex scatter-gather descriptor to write any piece of memory to different parts of the object. It also supports distributed transactions that are serializable to guarantee that the data model implemented by the I/O middleware is always consistent. The DAOS transaction offers database semantics and will allow to support SQL over DAOS. libDAOS is also very extensible, and new type of object can easily be added in the future if needed. As represented in this diagram, libDAOS is the new foundation to implement the I/O middleware. For instance, a parallel file system implementing POSIX semantics has been developed as a library directly on top of libDAOS and is called libDFS. This is the path to support all legacy applications running directly on top of POSIX. While all applications can effectively run on top of this parallel file system, we have been working with many partners to accelerate many I/O middleware and big data framework natively on top of DAOS. For instance, there is an HDF5 DAOS Vol connector built natively on top of libDAOS that offers more performance but also more functionality like snapshot of HDF5 file. We have also contributed an MPI-IO driver for DAOS, which is integrated into MPitch, Intel MPI, and soon other MPI version. The Hadoop API has also been emulated over DAOS and will provide a Hadoop file system connector that can be integrated directly with Apache Spark and Apache Hadoop. This allows, for instance, Apache Spark to load data directly from DAOS and write output data to DAOS. We also have a special shuffle plugin that allows to offload the shuffle phase of Apache Spark to DAOS. This was demonstrated at ISC and SC and offers a significant performance improvement over native Spark. We also have a TensorFlow-IO plugin that integrates DAOS natively with TensorFlow-IO and native Python bindings that allow to export the DAOS array and key value store directly to the Python language. This allows, for instance, to manipulate a super large Python dictionary with a zero memory footprint into the application, since the Python dictionary is effectively stored on the remote DAOS node. There is work underway to integrate those Python bindings directly with PyTorch. Over time, we also gained traction with several industry partners to integrate the DAOS API with very specific domain data model. Here they are represented in yellow, and there are only 4 examples. SEGY for oil and gas industry, FDB, which is field database, which is in collaboration with ECMWF to represent their climate data natively on top of DAOS. In collaboration with CERN around the root format, which is used for particle physics, and also trying to stream data from Atlas experiment directly to DAOS through this DAQ data acquisition layer. We are also collaborating with several partners who want to use DAOS more in the enterprise or cloud space as a safe replacement and need S3 layer on top of DAOS, for instance, by reusing the Rados gateway. And there is also work on the way to provide a native block interface on top of DAOS for virtualized environment. All those middleware provide a pretty rich software ecosystem that will continue to grow in the coming years. Traditionally, HPC storage systems tend to be optimized for write workload, assuming that HPC workload is mostly write intensive. With the emergence of AI and big data, this assertion is no longer true. That's why several optimizations were implemented in DAOS to optimize read bandwidth and IOPS. For instance, no parity check are done on read. Instead, DAOS use the checksum stored along with the data to validate the data. A dataset can also be replicated over many servers, and DAOS can read from any of those replicas, allowing to sustain way higher IOPS and bandwidth on read. As presented in the previous slide, we also did a very tight integration of DAOS with AI framework in order to remove all system call and also deliver more performance higher up in the stack. We are also working on a new feature called warm containers, write once, read many containers, that will allow for further optimization, knowing that the data is immutable. This involves aggressive caching on the client side, since we know that the data are not going to be modified. Also, an optimized representation of the data on the specific layout, and also size optimization for those immutable files. Maintaining file size is a very complex issue in POSIX and distributed storage systems, but this is obviously way easier if you know that the data is immutable. And again, all of this is possible because we have this notion of dataset, and we can have special treatment on a per dataset basis, which is difficult to do with a general purpose parallel file system with a single main point shared by all the users. The last architecture choice I would like to present today is targeted at workflows. It's very common for workflow to synchronize through the storage systems. Unfortunately, they don't necessarily have the primitives and the API to be able to do that efficiently. Workflow then tend to work around the limitation by abusing the namespace or copying the data many times. We try to address this issue in DAOS through a publish-subscribe API based around the notion of snapshot of a container. In this example, you have a basic producer-consumer pipeline where the producer is writing new data to a container at version 10. Once the producer has written a consistent new set of data to the container, then it can commit version 10, which effectively create a new snapshot v10 of the container. The consumer, on the other hand, would like to consume the data generated by the producer and can subscribe to the next available snapshot. It is going to be notified when version 10 is available and can then read the dataset at version 10. Since DAOS is a fully version storage system, the producer can continue to write at v11 without generating any conflict. The consumer also read from the snapshot and see immutable data that are not impacted by the write of the producer. Once the producer has submitted and completed all the I/O, then it can commit v11 and the consumer will then be able to subscribe again and be notified that a new version of the dataset is available. At that point, the producer can continue to write v12 and so on. v11 can then be consumed by the consumer from scratch or by querying the diff between v10 and v11. DAOS is indeed able to generate the list of objects and extent that have been modified between the two snapshots v10 and v11. Unfortunately, this is sometimes difficult for consumer to be able to parse this and interpret this information, and not many middleware are capable of using this functionality yet. But this is a very promising feature that I hope will be more widely used in the future. This framework can also be used for incremental backup or maintaining a copy of the data on an external tier up to date. In terms of future direction for DAOS, we would like the DAOS system to be more capable and not just move data from point A to point B. We are thus working on what we call the DAOS Pipeline API that allows to offload data-intensive processing to the storage node directly. The processing to be performed can be hard-coded in the engine and be predefined, or can also be user-defined by leveraging UBPF, which is the user space version of eBPF, which is widely used in the Linux kernel. This will provide a flexible and powerful interface without compromising security. As represented in the diagram, the intent is to be able to support reduce operation, filtering, but also transformation on a per dataset basis. The intent is to be able to leverage hardware accelerator whenever available on the storage node. This includes any accelerator, GPU, FPGA that might be available on those nodes, SmartNICs, but also computational storage devices, if any. There are many use cases, more particularly with AI frameworks, that usually need to prepare, pre-process, transform the dataset before it can be consumed. It will also, for instance, allow scientific application to calculate the minimum, maximum, sum, and average value over a very large dataset. Or, for instance, do floating point conversion. To demonstrate the capability of this API, we'll be working on two use cases. The first one is to try to offload POSIX find to the storage node by running the find filtering function directly on the storage node out of PMM. And we also have a MariaDB DAOS engine that today does all the filtering on the compute node. So all the data transits through the network. And we are working on a version of this DAOS MariaDB engine that will offload part of the SQL query on the storage node, transferring over the network only the filtered data and not more. On the business side, we have been able to create a pretty broad partner and customer ecosystem with big HPC vendors like HP and Lenovo actively involved into the DAOS community. We also have many reseller partners with the Intel DAOS team covering for the L3 support. Crowit offers a platform that can run either safe or DAOS and has been pretty active as well. And we have been also working very closely with several CSPs like Google Cloud to integrate DAOS into their marketplace. In terms of deployment, DAOS is deployed at the Eugene Hospital, at JINR, and also at the University of Cambridge. We are also now working on the LRZ deployment of a 1 petabyte DAOS system, and also DAOS will be the primary storage tier on the Aurora system at Argonne National Laboratories. Aurora is an Exascale cluster that will be deployed at Argonne National Laboratory in the US. It is a very large-scale system with more than 9,000 nodes. DAOS will be the primary storage for the Aurora cluster. The Aurora DAOS system will be composed of 1,024 DAOS nodes. Each DAOS node will be dual socket system with 512 GB of RAM, 8 TB of Optane persistent memory 200, and 16 NVMe SSD for a total NVMe SSD capacity of 244 TB per node, and 2 HP Slingshot cards to connect to the high-performance fabric. The total capacity of the DAOS system will be 249 petabytes without data protection, or 220 petabytes with erasure code. This large DAOS system will be able to address the needs of the most demanding HPC and AI application running on the compute node of Aurora. Once the deployment completed, the DAOS installation on Aurora should be one of the biggest storage systems on the planet. As mentioned before, DAOS is completely open source and we deliver regular community releases. To date, we deliver DAOS 1.0, 1.2, DAOS 2.0, and bug fix releases for DAOS 2.0. We are now working on DAOS 2.2 version that should be released in the first half of 2022. DAOS has a built-in interoperability framework to be able to upgrade from version 2.0 to 2.2 at subsequent version. We are then on the cadence of 2 major releases per year with bug fixes as needed. 2.2 will have the support for Rocky Linux 8.5 and will drop CentOS 8 support. Add support for Mellanox UCX and switch from the socket provider to the TCP provider, and include several user experience improvements, like support for Intel VMD to be able to manage the LED on the SSD, some pull creation improvement to be able to specify the percentage of the pool that you want to create. And in DFS, M time will be accurate. In 2.4, we will move from LEAP 15.3 to 15.4 and to Rocky Units 8.6. We will then officially support Mellanox UCX in production and provide tech preview for the OPX provider from Cornelis Networks. Looking forward to platform enabling PCIe Gen 5, we will be able to support more SSD per node. We will land support for checksum scrubbing in the background and fix a few remaining issues for online drain and reintegration and add. 2.4 will also support SSD hot plug, LED management over VMD, diffuse multi-user, and several optimization with the interception library, as well as the Lustre integration. In 2.6, we'll officially support the OPX provider, add support for multi-providers through multi-home network support, and land the catastrophic recovery mechanism which is under development, which is basically similar to online file system check. We will also provide several optimization for future Xeon platform like DSA. 2.8 will add a network topology awareness into the DAOS placement, some online resizing of the pool, advanced steering support, and inline compression through the Intel Quick Assist technology. We will also provide a framework for the middleware to write their own file system check. We will then look forward to DAOS 3.0 in 2024. As an open source project, DAOS has a lot of materials available online. The source code is available on GitHub on the DAOS Slack organization under DAOS. We have online documentation on docs.daos.io. We have a pretty active mailing list and Slack channel that you can join through daosgroups.io. And we also post regular YouTube video to present DAOS or explain how to deploy it or for specific areas. Every year we have a user group combined with SC, and all the recording of the last user group from the DUG21 is available online. We have an upcoming BOF at the ECP annual meeting, the week after the ECP meeting actually, and also a BOF at ISC, and we also have a link to the Intel landing page. Thanks for your time, and I will welcome any question.
Thank you so much, Johann, for that deeply informative session on DAOS. I see there was a question which was asked in the chat, and I believe you have answered. I'm just going to show it on screen. How do you plan to the roadmap for DAOS in general in terms of releases? And I believe there has been a detailed answer, but I just wanted to show this up on screen. Would you like to add something to that, Johann?
Yeah, I mean, we don't use GitHub issues because we are doing a lot of agile process internally, and Jira is a well-known reference to manage dashboard and so on. So we don't use GitHub issues. We only use GitHub for managing the source code, PRs, and so on. Right. And our Jira is public. Yeah, everything is public, is accessed. Right. I mean, to post, to be able, you need to create ticket and so on. You need special permission, but right. Anybody can create an account.
Oh, that's great. But it's good to know that you are maintaining everything in the public domain, so that way it's still something which everybody can access, right? Yeah.
Yeah, it's a Jira cloud, so we use the infrastructure put together by Confluence. Yes.
Yeah. I believe that's all the time we have. Thank you so much, Johann. It's always a pleasure to listen to you. Your talks have always been detailed and very informative, and we hope to continue this collaboration in all future events.
Thanks for the invite. Bye.
Yeah. Bye-bye. We will see you in the next session.